Hello everyone, welcome to the OneClass channel. My name is Millen and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university level. If you're interested in getting some help with your homework or if you're interested in tutoring, check out the links in the description below. Cool, so I'm going to switch over my screen real fast and we can start this physics experience. Cool, so let's get this party started. Okay, so the first question that we got on the menu today is asking us, we have two identical capacitors that are connected in parallel to an AC generator that has a frequency of 660 Hertz. That produces a voltage of 24 volts. Okay, the current in the circuit is 8 amps. Now we have to find the capacitance of each capacitor. Okay, this is a pretty cool question. Let's first start out by drawing out what this circuit is. So it said two identical capacitors that are connected in parallel. So here we can draw that out by doing something like this. Okay, so this can be capacitor 1, this can be C. And this can be capacitor 2, that's also C. And they are connected in parallel like this. Okay, parallel capacitors, exactly what they look like. And we have a AC voltage source. So AC voltage sources, typically you draw them like this. And we know that this is going to be 24 volts. It's going to have an AC frequency of 660 Hertz. 660 Hertz. And and the current going through this whole circuit is 0.8 amperes. So let's call this I is equal to 0.8 amps. Okay, now we're trying to find values of capacitors. Okay, so this is a diagram of all the necessary information that we can extract from the question. Now we can make some simplifications to make our life a little bit easier. So here I've identified a situation here. In this red circle we have parallel capacitors. Now, parallel capacitors, the way that you get like an equivalent capacitance out of them is pretty similar to how you do series resistors or series inductors. So, for parallel capacitors, this is the equation. The equivalent capacitance is simply all the component capacitances Ci added together like this. Okay, so in this case CEQ, so if we were to compress these two capacitors into a single capacitor, we would just get 2C. Okay, nice and easy. So let's redraw the circuit. So let's redraw knowing CEQ. Okay, this should be nice and straightforward. So our voltage source is going to be the same, as well as our current also going to be the same. So we're going to have our AC voltage source 24 volts at 660 Hertz. It has a current through the circuit 0.8 amperes. That would be I. And here we have CEQ. I'll write CEQ, but we also know that this is equal to 2C, and we're trying to solve for C. Okay, so the question, what we have here is they use reactance, but in my opinion, I feel like it's better to use inductance, because inductance will be valid for when you also have resistors in the circuit at the same time, but in reactance would not necessarily be appropriate if you had both storage elements, like if you had resistors and inductors or resistors and capacitors, you would need to use inductance for that. So reactance is very specific to when you only have storage elements, meaning inductors and capacitors. So let's find the impedance. Let's use impedance instead because it is more universal. Okay, so we need to get impedance. Get impedance of capacitor. And for those of you who are maybe unfamiliar with impedance, impedance is essentially like resistance but complex. So impedance is basically just resistance in complex form. Okay, cool. So we know that impedance of a capacitor impedance looks like this. So Z, we use Z or Z. In Canada, we say Z for the last letter of the alphabet. But ZC, or the impedance, Z or Z, represents impedance. I'm going to say Z because that's what we say in Canada, but a lot of places also say Z for that. Interesting quirk of language. But the equation for that, to calculate the impedance of the capacitor, is 1 over J omega C. And omega is the omega is angular frequency. And J is the complex term. And it's not really relevant for this particular circuit. So, but, just keep in mind that it is there. You do need to be kind of familiar with complex numbers, but just keep in mind that this is the complex term. Not really relevant. For this particular circuit. Okay, so the angular frequency, we know that this is 2 pi times F. And F is equal to 660 hertz. So our omega term here, this has got to be, what we have here. We're going to have 2 times pi times 660 hertz. Now I'm gonna put that into my handy dandy calculator because my quick maths are not that quick. 2 times pi multiply 660, and we get this is equal to 4146.9 radians per second. Okay, so let's substitute in some of these numbers into our equation here. So I'll actually switch up the color. So blue for capacitance. So now when we actually want to find the ZC, the impedance of this circuit, which is really just the impedance of the capacitor, we're going to do 1 divided by J, multiply that by omega, which is 4146.9 radians per second, multiplied by 2C. Right? Because that's the equivalent capacitance of every capacitor in the circuit. Okay? So we definitely cannot forget that 2 term. Okay? So, send that into the calculator and see what we get. It's really just multiplied by 2. So we get Z over C is equal to 1 over J times 8,293.8 farad radians per second. The unit is not super important. I'm just writing it out to be formally proper, but if you're rushing, you don't really need to focus on that. Okay, now this is the impedance value that we're going to use. Okay, so we know that since impedance is basically just resistance in complex form, we know through Ohm's law. Oh wait, I got to attach the C at the end of here, right? Because the C is the variable that we're trying to solve for. This is our target variable. Okay, now we know from Ohm's law, I'll put this in orange. Does that appear well? Yeah, okay. Ohm's law also applies for impedance and AC voltages and currents. Okay, but we'll need to find the magnitude of them. All right, so the magnitude of this, so since, oops, I'll switch back out to blue because that's kind of more related to that. So since impedance is a complex number, convert to magnitude. Okay, now the magnitude here, it's very so you would do like real squared plus imaginary squared, all under the root. It's definitely got the same type of energy as good old Pythagoras. But since we just have the imaginary part, so the J is what's associated with the imaginary part. Whoever has a J factor attached to them, that's an imaginary term. Okay, so in this case, our ZC impedance magnitude, and magnitude is typically represented by like absolute value bars on either side of your variable. So once we surround it by that, well, in here for our ZC, our real component is just 0, so it's just gonna be like square it and then square root it. So for us, our ZC, our magnitude of ZC, is just gonna be the same, but the J is gonna disappear because, as we know, J is equal to the square root of -1, and when we square it and then neutralize it, like it's really, honestly, just avoid using J like period inside of your magnitude calculations. Okay, because you actually don't want to use your J at all in that calculation. You just take like the term associated with J. Okay, so for us in this case, this is really just going to be the same as 1 over 8 to 93.8 C. Okay, now we know since Ohm's law is telling us basically that we have V equals I Z. Remember, impedance, like resistance. And we be trying to solve for C here. And C is a component that makes up Z, so we want to isolate Z. So V over I is equal to Z, and we know that Z is going to be equal to 1 over 829.3.8 C. Okay, so now if we're trying to isolate C, isolate the C. You see what I mean? We will bring the C to the other side, and everything else can stay here. So C is going to be equal to I over V, and down here is going to be multiplied by 829 3.8, and subbing in our values, we get I is equal to 0.8 amps. That was a nice easy number, 0.8 amps. Our voltage is going to be 24 volts. And then we had this other term here of our 8,293.8. And then we math this out and we will find our capacitance. And that will be awesome. So let's ask our calculator to figure that out for us. 0.8 divided by 24 times 8293.8. And the result that I got was 4.02 times 10 to the negative 6 farads. Remember, capacitors always have the unit of farads, and that would make perfect sense here because I didn't write the unit here attached to that 8,000 term, but we know that it was like it was radians, farad, radians per second. Yeah, so I'm sure that would all work out, and we come to farads. And another way that we could write this is we can convert that to a micro farad. Whoops, I guess that'd be more like that. So we have C is equal to 4.02 microfarads. And that is a pretty reasonable answer. A lot of times you'll see capacitors that are measured in microfarads. So based on the magnitude of it, it feels like it could be a reasonable value. And it would seem that our result from the junior tutor here looks good, and we came to the same conclusion. And that's awesome. So just as a recap, we want to first simplify our circuit as much as we can, and then we found the impedance of the capacitor. Once we had the impedance of the capacitor, we could use that in Ohm's law, knowing the voltage and the current, and we used that and we could solve for C, which was the only thing that we needed to solve, and that's the value of the capacitor. And we realize now that we have to have 4.02 microfarads. That would be the only capacitor value that can make this description of a circuit valid. Okay, so here the above solution is good. That's awesome. Great stuff. Great work.